All right, let's take a look on how to integrate a multivariable function. So far we've seen how to take the derivative of a multivariable function. We use partial derivatives. So how do we integrate? Well, it's not called partial integration, but the idea is roughly the same. So let's just say if we were integrating some multivariable function, I don't know, how about 2xy cubed dx. Well, we use the same basic idea when we're integrating here. We're going to integrate this function with respect to x. That means that all y's are constants. Now, since this is a constant multiple, you could do this if you wanted to, like we can do with all constant multiples, and bring that out front. Now, of course, we would integrate this the same way that we always would when we integrate that with respect to x. That gives us an x squared, so that'd be x squared y cubed plus some constant, of course, our integration constant. Now, the integration constant's a little bit different now, because it's not just c like it used to be. We have to think about it in terms of partial derivatives. What could this be to where if we took the derivative with respect to x that it would go away? Well, a constant would work, but also, let me go ahead and change this so you can use c there if you want to. This would actually be any function of y, right? Because if it's a function with only y's in it, if you take the derivative with respect to x, this would go away completely. So notice we take the derivative of this expression with respect to x, we get 2xy cubed plus, and of course that would be 0. So anytime you integrate with respect to a letter, the integration constant is a function of the other letter. All right, let's take a look at what's called iterated integrals. Now, iterated just really means kind of like repeated, is one way to think about it. Or this is called multiple integration. Let's say we integrated the expression, I don't know, x squared y cubed dx dy, and just for fun, let's put some bounds on this. Let's go from 1 to 2. All right, this would be kind of messy. All right, this is called an iterated integral, or just multiple integration. You're actually going to think about it as two separate problems. We have an inside problem, which is just the integral with respect to x. We're going to get that answer, and whatever that answer is, we're going to integrate with respect to y. Now, one way you want to think about these bounds here, since the first integral is with respect to x, technically, and we generally don't write this, these bounds are for what x is equal to. And for the last integral, those for y, so these bounds are for what y is equal to. Now, we generally don't write the red part that I have up there, but it's a good way to think about it. So, if we're going to do this first integral, we're integrating this expression with respect to x. So, integrating that with respect to x, our y's are constant, so I get 1/3 x cubed y cubed. Now, we need to evaluate that from 0 to 1. And of course, whatever that answer is, we're going to integrate with respect to y. Now, again, for these bounds, these are the bounds for x's. So we're going to plug these in for x. So this is going to be the integral from 1 to 2, 1/2 1 cubed times y cubed minus 1/2 0 cubed times y cubed. All right, and we still need to integrate that with respect to y. Now, looking at this, let's see, we still get the integral here. This is just going to be, look, these are 3's. We get 1/3 y cubed, and of course that's 0 dy. Now it's just a calc 1 integral, integrate it the way you normally would. So that's going to be 1/12 y to the 4th evaluated from 1 to 2. So let's bring it up over here. So it's 1/12 2 to the 4th minus 1/12 1 to the 4th. So let's see, it's going to be 16. What is that going to end up being? So let's just go and write it out. So 2 to the 4th is 16 over 12 minus 1/12. So 16 twelfths minus 1/12 would be 15 twelfths. That'll reduce to 5/4. Okay, so an iterated integral is just an integral where you start integrating from the inside and work your way out. Complete the integral on the inside first, whatever that result is, then integrate it next. Now, this iterated integral only has 2 integrals. We could do it if it had 3 integrals or 4 integrals, doesn't matter. Just start with your inside integral, complete it, and work your way all the way out. All right, so how can we use this in terms of stuff that we've already seen? Well, let's take a look at a Calc 1. From Calc 1, we saw that we could find the area between two curves, let's say f of x and g of x. If, let's say the picture looks something like this. Here's our function f, there's a function g, and let's say we're trying to go from, I don't know, a to b. The way that we would find that area, let's see here, would be, remember, it'd be the integral from a to b, the top curve minus the bottom curve. So that would be f of x minus g of x dx. Well, here's something fairly interesting. Now, this is just a Calc 1 problem. Change this into an we can turn this into an iterated integral, or in this case, a double integral, because it's going to have two integrals here. Anytime we have something like this, a difference in here, or we can make a difference, we can actually turn that into an integral. Think about it like this. If we know something as simple as like the integral from a to b of dx is just what? That would be the b minus a once you simplify it. That means that we can turn this difference back into an integral. So for this up here, we have the integral on the outside, which is with respect to x. We have the integral from a to b dx. But what would this be? Well, this is telling us what y runs from, right? Y runs from g to f. So we could say that's the integral of g of x to f of x, slide it over a little bit more, dy dx. Now notice that this is going to give us an area, just like before. This is an area. And you can see it over here in our argument. We have 1, there's an understood 1 there, an x times a y, or a length times a width, so this would give us the area between two curves. Between f and g from a to b. Now, of course, this is assuming from our picture that f and g don't change places, like which curve's on the top and which curve's on the bottom. So when we set up a region like this, we can actually find the area of a region using a double integral. All we got to do is determine what one variable runs from and what the other variable runs from. So let's see if we can do an example, something that we could do easily in Calc 1, but let's see if we can set it up like this. So what if I said, find the area of the region bounded by, let's say, y is equal to the square root of x, y equals 0, and x is equal to, I don't know, 4. Now, just so we can see it on here, let's take a quick little look at this. Of course, the square root of x looks like that, goes on out forever. Y equals 0 is the x-axis, that's here. And x equals 4 is the vertical line here. So it's this little region in here I want to find the area of. Okay, now if we're going to do a double integral for this, we need to determine which direction we want to do this. Now, back when we were doing like volumes of revolution and stuff like that, we would put a representative rectangle in there. It's not a bad idea, so you can kind of see which way we were going to do it. If we're going to do it this way, let's say we're going to set it up with our double integral. Here we're basically talking about what y values do does our integral run from, or this rectangle run from. Well, the lowest y value is what? Y equals 0 up to the y value of y equals the square root of x. So this would go from 0 to the square root of x in the y direction. And then what does x run from? X goes from 0 to 4. So it goes from 0 to 4 in the x direction. Now here, it could be fairly helpful, and again, we don't normally write it, that's why I'm doing it in red here. Remember, the first bounds are what y equals, the second bounds are what x equals. Okay, so that would give us the area of this region. Now, if we do the very first step, if we go ahead and do the first step, we're going to see if we get the same thing that we would have in Calc 1. If we integrate with respect to y, well, just one, we get y evaluated from 0 to the square root of x dx, which is 0 to 4 top endpoint minus the bottom endpoint, or just the integral from 0 to 4 the square root of x dx, which is generally what we would say that the area of this region would be. And of course, you can figure out whatever that is. So we can use a double integral to find area. And believe it or not, sometimes it's easier to look at the region as two different directions. Now we had an option here. We set this up going in the y direction, then the x direction, but we could also go in the x direction, then the y direction. Now the idea here is, kind of like this, our representative rectangle is kind of going in this direction. Okay, so what does the x value run from in this region? It runs from this curve to this curve. So what does x equal? Well, this curve's easy. This is the curve x equals 4. This one's a little bit different. What does x equal here? Down there, x is equal to y squared. So if we were to set this up, the x values go from y squared, x equals y squared, over to x equals 4. So this is y squared to 4. Now what does y run from in this region? Well, y runs from 0 up until, well, if x is 4, that means y is 2. So this would go from 0 to 2. Now this will give us the exact same answer. If you don't believe me, go through and work it out. Sometimes it's easier to work in doing dy dx, and sometimes it's easier to work with dx dy. Sometimes it's about exactly the same, so it's not that big a deal. But there are cases that it will only work in one direction and not another. So you're going to want to make sure that you know how to flip the order of integration. All right, let's take a look at one more thing that the author may ask you to do in a section like this. Sometimes they'll give you an iterated integral and say, sketch the, I'll just say given region. So let's say we had a double integral here that goes from, I don't know, 0 to 2x and from 1 to 2, and of course this would be dy dx. All right, now when we're setting up these integrals, let me point out something here real quick, and this will be more apparent in our in future homework, it's not so much right now. When you're setting up bounds for integrals, since our first integral here is dy, these bounds can only contain variables that are to the right of it. So these bounds, since this is dy, these bounds can only contain the letter x. And if we look at the next integral, that's with respect to x, since it doesn't have any variables to the right of it, these bounds cannot contain variables. We take a look at this integral. This is integral with respect to x. The variable to the right is y, so these bounds can only contain y's. And if you look at the y's, there's nothing to the right of it, so that bounds can only contain numbers. All right, so here, if you notice how it's kind of set up again, our first integral is with respect to y. The only variable to the right of it is x, so these can only contain numbers and x's. The next integral is with respect to x. There's no variables to the right of it, so these bounds can't contain any variables. All right, so if we're told to sketch this region, let's see if we can do this. So remember, these are the first ones are the bounds for y. So this basically says our graph's going to go from y equals 0 to y is equal to 2x. So let's do a real quick sketch of that real quick. Y equals 2x, well that's just a line with a slope of 2 over 1 up 2, goes through something like that. Like that. And so we're thinking from the y equals 0 up to here. Now for the x, we have x equals 1 to x equals 2. So that's x equals 1 to x equals 2. So the region that we're talking about from here to here, between y equals 0 and y is equal to 2x. So that right there would be the region described by this double integral. All right, let's take a second and just kind of summarize a little bit of this and see how we can generalize the concept of multiple integration. and what it can represent. Now, these can always represent other ideas. This is just basically for the normal things that we see. From Calc 1, if we're doing the most basic integral, the integral from like a to b dx, well, that's just b minus a. And if you think about that integration, we're only integrating in one direction from a to b. And when you do b minus a, you end up with the length between b minus a. So this is a length. Then in Calc 1, we said basically the same thing. We said the integral from a to b of f of x dx. Now notice our argument now is a function of x. It's the subtle things that get by us. Remember, f of x represents a y value. So now we have an x times a y, or a length times a width, and we saw in Calc 1 that this gives us an area. Now, from today, we saw that we could take this argument here. I'm going to change it just a little bit. That's from a to b. We could go from, you can think about this as a difference if you wanted to. This is f of x minus 0. So I could do this. I'm going to change it in a second. That would actually represent it, dy dx. But generically speaking, by the way, this would be the same. But generically speaking, it can be any function of x down here as well. Here we still have just 1 times x times a y, so this still represents an area. So extending the idea a little bit more, let's see, I have to move up there in a second. What if I had the integral from a to b, the integral of g of x to f of x, times some other function of x and y, dy dx. See, I can integrate this because it has the variables. All right, so what does this? Well, in our multivariable world, a function in x and y is generally denoted by a z direction. So now what do we have? We have x times y times z, or a length times width times a height idea, which means this would be a volume. So if we have a double integral with an argument in here, that's generally going to give us a volume. Now, using the exact same trick as before, I can turn this argument into an integral. So the way that we have it written, I'm going to move it up here. The x's would still go from a to b. The y's still go from g of x to, what did I say, f of x. Now again, if I was to actually represent this, this would be 0 to h of x and y. But generically speaking, let's see, let's call it j. Now, since that's a z value, this would be dz, dy, dx. This would also represent a volume. Now, a few things to note. Since the first integral is with respect to z, the letters to the right of it in this case are y and x, and notice the bounds can only contain y's and x's. The next integral is with respect to y. The letter to the right of it is an x, which means these bounds can only contain x's. The x is the last integral. There's no letter to the right of it, so the bounds cannot have x's in it. Now, this is really what we're going to do for a large part of the rest of this chapter, is taking a look at all these different situations where we're going to turn single integrals into double integrals into triple integrals to represent length, area, and volume.